January 17, 1943, somewhere over the frozen coast of Tunisia. The morning sun cuts through thin clouds at 28,000 feet, casting long shadows across the Mediterranean below. Oberleutnant Franz Schiess pulls his oxygen mask tighter against his face, the rubber cold and stiff in the high-altitude air. His Messerschmitt Bf 109 G6 hums with mechanical precision beneath him, the Daimler-Benz engine's 1,200 horsepower, a familiar song after 2 years of combat. Below, American bombers crawl across the sky like insects, their contrails writing temporary scripts against the blue canvas. Schiess adjusts his gun sight, calculating deflection angles with practiced ease. He has 43 confirmed kills painted beneath his cockpit canopy. 43 Allied aircraft sent spiraling into the earth or sea. Today should add one more. Then he sees it, a shape that doesn't belong in his mental catalog of enemy aircraft. Twin booms extending back from a central nacelle, twin engines, a profile that looks like someone took two fighters and welded them to opposite sides of a cockpit. The American P-38 Lightning. Schiess has heard stories about these strange machines from other pilots, dismissive stories told over schnapps in officers' quarters. The Americans and their engineering excess. Two of everything when one would suffice. Typical wasteful abundance from a nation that builds refrigerators and automobiles instead of proper fighting machines. The P-38 is heavy, the stories say, clumsy in a turning fight, easy prey for a skilled pilot in a 109 or a 190. Schiess pushes his stick forward slightly, beginning a shallow dive to gain speed for the attack. He expects the twin-boomed oddity to see him, to turn and run, or perhaps foolishly attempt to dogfight. He expects to use every lesson learned in the skies over France, Britain, and Russia. He expects victory. What Franz Schiess does not expect is for the P-38 to roll inverted and dive straight down at a speed that makes his own aircraft seem to be standing still in the air. What he does not expect is to push his own stick forward in pursuit and feel his Messerschmitt begin to shake, then shudder, then buck like a wild animal as the air over his wings becomes turbulent and uncontrollable. What he does not expect is to watch helplessly as the American fighter pulls away from him in a vertical dive, growing smaller and smaller until it levels out 6,000 feet below, unscathed, while his own hands fight the controls to prevent his aircraft from tearing itself apart. Franz Schiess does not expect American engineering to rewrite the rules of aerial combat at the precise moment he believed he understood them completely. The story of how American engineers accomplished what German aerodynamicists considered impossible begins not in the skies over North Africa, but in the quiet desperation of 1937, when Europe's slide toward war seemed inevitable and America's military aviation lagged a generation behind. The United States Army Air Corps operated fighters with fixed landing gear and open cockpits, while German factories were already producing all-metal monoplanes with retractable wheels and enclosed canopies. The gap was not merely technological, but philosophical. German aviation grew from military necessity and state direction. American aviation grew from commercial competition and civilian innovation. These different origins would produce aircraft with fundamentally different strengths, different assumptions built into their very airframes. In February 1937, the Army Air Corps issued a specification for a high-altitude interceptor capable of reaching 36,000 feet and maintaining combat capability at that extreme altitude. The requirement was extraordinary for its time. Most fighters struggled to reach 25,000 feet. The specification demanded not just altitude, but speed, firepower concentrated in the nose rather than scattered across wings, and range exceeding that of any existing fighter. It demanded, in essence, an aircraft that did not yet exist anywhere in the world. Multiple companies submitted proposals. Most were conventional single-engine designs stretched to their limits. Lockheed Aircraft Corporation, A relatively small company, known primarily for commercial transports, submitted something different. Chief Engineer Hall Hibbard and his young assistant Clarence Kelly Johnson proposed a twin-engine, twin-boom design that placed the pilot in a central nacelle between two Allison V1710 engines. The engines would drive counter-rotating propellers to eliminate torque. The twin booms would extend back from the engines to carry the tail surfaces. All armament would concentrate in the nose, directly in front of the pilot, where convergence problems disappeared. The design was radical. The design was unorthodox. The design was precisely what American engineering did best, solving a problem through unconventional thinking rather than incremental refinement. The prototype XP-38 first flew on January 27, 1939. Test pilot Ben Kelsey pushed the aircraft to 413 miles per hour during the flight, faster than any American fighter had ever flown. The Army was impressed enough to order 13 service test aircraft, but impressive demonstrations and actual combat capability existed in different worlds. The P-38's development would stretch across 4 years, through multiple variants, through problems that seemed insurmountable, and modifications that seemed endless. Early production P-38s suffered from tail buffeting that made them unflyable at high speeds. The engines overheated. The cockpit froze at altitude despite being enclosed. The turbochargers failed. The counter-rotating propellers required different spare parts for left and right engines. Armament installation proved complex. The list of problems seemed to grow faster than solutions appeared. German intelligence officers, reading reports about the P-38's troubled development, added the aircraft to their catalog of American failures. Another example of democratic chaos producing expensive, complicated machines that looked impressive on paper but crumbled in combat reality. They were wrong. They were fundamentally, catastrophically wrong. But understanding why requires understanding a phenomenon that German aerodynamicists in 1941 were only beginning to comprehend: compressibility. When an aircraft dives, it accelerates under gravity's pull. As speed increases, the air flowing over the wings accelerates even faster, particularly over the upper wing surface, where airflow must travel a longer distance. At a certain speed, this accelerated airflow approaches the speed of sound. When it does, the air's behavior changes fundamentally. Instead of flowing smoothly over the wing, it forms shock waves, turbulent boundaries where the air's pressure and density shift abruptly. These shock waves separate the smooth airflow from the wing surface. The wing stops generating lift. The tail surfaces stop generating control authority. The aircraft becomes uncontrollable, locked into a terminal dive that usually ends with the aircraft breaking apart from aerodynamic stress or impact with the ground. Pilots called it compressibility. Engineers called it transonic flow effects. Everyone called it deadly. Every high-performance fighter of the Second World War encountered compressibility problems. The Messerschmitt Bf-109 began experiencing control difficulties in dives exceeding 450 miles per hour. The Focke-Wulf Fw-190, Germany's newest fighter, fared slightly better, but still hit a wall around 500 miles per hour where the controls froze and the nose pitched down uncontrollably. The British Supermarine Spitfire encountered similar limits. The Japanese Zero, built light to maximize maneuverability, couldn't survive the structural stress of high-speed dives even before compressibility effects appeared. These limitations were accepted as fundamental laws of aerodynamics, boundaries that current technology couldn't cross. German pilots learned to never follow an enemy into a straight vertical dive. Recovery might prove impossible. The tactic became doctrine: never pursue vertically, force the enemy to turn, win through maneuverability rather than speed. American engineers at Lockheed encountered compressibility problems with the P-38 during flight testing in 1941. test pilot Ralph Verdon dove a P-38E to high speed during a demonstration flight over Burbank, California. The aircraft entered compressibility, the tail began buffeting violently, and the nose pitched down beyond Verdon's ability to control. The P-38 continued diving until it impacted the ground, killing Verdon instantly. The crash investigators found an aircraft that had been structurally intact until ground impact. The problem wasn't strength, the problem was aerodynamics, the air itself becoming an enemy at high speeds. Kelly Johnson and his engineering team faced a decision point. They could accept compressibility as an insurmountable barrier, limit the P-38's diving speed, and join the consensus that fighters simply couldn't exceed certain velocities. Or they could attempt something no one had successfully done, modify an existing aircraft design to push through the compressibility barrier. They chose to push through. Between 1941 and 1943, Lockheed engineers developed a solution both elegant and unprecedented. They designed dive flaps that extended from the underside of the wings. These weren't ordinary flaps meant to increase lift for landing. These were dive recovery flaps, specifically engineered to disrupt the airflow over the lower wing surface during high-speed dives. When deployed, they changed the pressure distribution around the wing in a way that delayed the formation of shock waves and maintained airflow attachment at speeds where other aircraft lost control. The flaps gave pilots a tool to recover from compressibility-induced dives. More importantly, when properly used, they allowed the P-38 to dive faster than any other fighter in operational service. The modification began appearing on P-38J models arriving in combat theaters in mid-1943. German intelligence noted the addition of small flaps to American P-38s. They did not understand their purpose. They did not realize that American engineering had just rewritten the tactical capabilities of air combat. Franz Schiess and thousands of German pilots like him learned about dive flaps the hard way. The Messerschmitt Bf-109 remained an excellent fighter in turning combat. It could outturn a P-38. It could outclimb a P-38 at low altitudes. In a horizontal scissors maneuver or a vertical rolling fight, a skilled German pilot had excellent chances against the heavier American twin-engine fighter, but American pilots stopped fighting that way. Why engage in a turning fight where the enemy held advantages when you could use speed and altitude to dictate engagement terms? P-38 pilots developed tactics that leveraged their aircraft's unique capabilities. Fly high, above the German fighters. Wait for the right moment. Then dive, building speed that no Luftwaffe fighter could match. Make one firing pass at speeds exceeding 500 miles per hour. If the pass connected, the target was destroyed. If it missed, continue the dive, pulling away from any pursuit, then use the P-38's excellent climb rate to return to altitude and repeat. Never dogfight. Never turn with the enemy. Use the engineering advantage that Lockheed's dive flaps provided. The psychological impact on German pilots exceeded the tactical impact. These men were trained to believe in their aircraft's superiority and their own skills' supremacy. They flew machines designed by engineers who understood aerodynamics, built in factories that represented Europe's industrial pinnacle, flown by pilots with combat experience stretching back to the Spanish Civil War. They expected to dominate the sky through superior technology married to superior training. The P-38 shattered this expectation in the most visceral way possible. It wasn't that the P-38 was better at everything. In pure turning combat, the German fighters maintained their edge. It was that the P-38 refused to fight the kind of battle the Germans were prepared to win. It exploited an advantage that German engineering had declared impossible to achieve. This was psychologically corrosive in ways that simple defeat was not. Simple defeat could be explained through bad luck, numerical superiority, or individual mistakes. Being outrun in a dive couldn't be explained away. It was engineering. It was American engineering, which German propaganda had spent years dismissing as inferior to German precision and thoroughness. Lieutenant Colonel Cass Howe, writing in a tactical assessment dated November 1943, observed, "The enemy has learned not to follow P-38s in the dive. Our pilots report that German fighters will pursue to approximately 20,000 feet, then break off engagement even when in favorable position. This represents a fundamental shift in enemy tactics." The language is dry, bureaucratic. The implication is revolutionary. German pilots were abandoning potentially successful attacks because they feared what would happen if the engagement became a diving contest. Fear was entering the tactical equation, not fear of death, which all combat pilots learn to manage, but fear of helplessness. Fear of pushing your stick forward in pursuit and feeling your aircraft begin to shake itself apart while the enemy pulled smoothly away. Fear of discovering that your 2 years of training and your 50 missions of experience counted for nothing when the fight entered a flight regime your aircraft couldn't survive. The accounts from German pilots who survived encounters with diving P-38s carry a consistent theme of shocked disbelief. Hauptmann Emil Clade, a decorated pilot with 61 confirmed victories, wrote in his combat diary after an engagement over Italy in January 1944, "The American dove away, as they always do. I followed, confident in my 190's speed. At 6,000 meters, the controls began to stiffen. At 5,000 meters, I could barely move the stick. The American was still diving, still pulling away. I had to break off or face structural failure. This is not combat. This is physics defeating courage." Clade's words reveal the deeper wound. German pilots were trained to see aerial combat as a contest of skill, courage, and will. The P-38's diving capability removed those human factors from the equation. It made aerial combat a simple matter of engineering specifications. The aircraft with better transonic characteristics won, regardless of pilot skill. This was unacceptable to men who defined themselves through their mastery of a difficult craft. The engineering achievement that made the P-38's diving capability possible wasn't a single brilliant innovation. It was systematic, methodical problem-solving applied across multiple overlapping challenges. The dive flaps solved airflow separation. But dive flaps alone weren't enough. The P-38's airframe had to survive the aerodynamic loads of high-speed flight. Lockheed engineers strengthened wing attach points and boom structures. They modified the empennage to reduce flutter. They changed elevator boost mechanisms to give pilots the muscle to recover from high-speed dives. Each modification required testing, analysis, redesign, and more testing. The process consumed thousands of engineering hours and tens of thousands of test flight hours. This was American engineering's particular genius, not brilliant individual insights, but organized, systematic application of scientific method to practical problems. German engineering produced elegant solutions to narrowly defined problems. American engineering produced workable solutions to broadly defined challenges. Both approaches had merit. In the specific case of transonic flight characteristics, American methodology proved superior because the problem was too complex for elegant theory alone. It required empirical testing, failure analysis, and iterative refinement. By the summer of 1944, P-38s equipped with dive flaps were operating across every combat theater where American forces fought. Over Europe, they escorted heavy bombers deep into Germany, their range exceeding that of single-engine fighters, and their speed making them difficult prey for intercepting German fighters. Over the Pacific, they hunted Japanese aircraft across vast oceanic distances, their twin-engine reliability providing crucial redundancy when operating hundreds of miles from the nearest friendly base. The most successful American fighter ace of the war, Major Richard Bong, with 40 confirmed victories, flew P-38s exclusively. So did Major Thomas McGuire, the second highest-scoring American ace, with 38 victories. The list of P-38 aces extended to dozens of names, pilots who learned to exploit the aircraft's strengths while avoiding its weaknesses. They flew high. They dove fast. They fired their nose-mounted guns in concentrated bursts. They climbed away before the enemy could respond. They won through engineering advantage as much as through pilot skill. The symbolic significance of the P-38's diving capability extended beyond tactical advantage. Every German pilot who broke off an attack because he feared compressibility was implicitly admitting that American engineering had solved a problem German engineering considered unsolvable. This admission corroded the ideological foundation that supported German military confidence. Nazi ideology taught technological and organizational superiority of the Germanic peoples. It taught that democracy produced chaos and that capitalism produced waste. The P-38 proved these teachings wrong in the most tangible way possible. A democratic nation with a capitalist economy had produced a fighter aircraft that outperformed its totalitarian counterparts in a crucial flight regime. The aircraft had been designed by a small California company, not a state arsenal. It had been refined through commercial competition and military feedback, not through central planning. It represented everything Nazi ideology said shouldn't work, but which manifestly did work and worked better than the German alternative. This ideological challenge appeared in unexpected places. German technical intelligence officers produced detailed reports on captured P-38s. These reports analyzed the dive flaps, the structural reinforcements, the engine installations, the armament arrangement. They were thorough, professional, technical. They were also suffused with a tone of grudging respect bordering on admiration. One report from the Rechlin Test Center, dated April 1944, noted, "The dive recovery system represents an innovative solution to transonic flow separation. While increasing drag and mechanical complexity, it provides operational capabilities our current fighter types cannot match." Recommendation: urgent development of equivalent system for BF-109K and FW-190D models. The recommendation went nowhere. By April 1944, German aviation industry was struggling to maintain production rates under constant Allied bombing. Resources didn't exist for major airframe modifications. German fighters would fly without dive flaps until war's end. German pilots would continue breaking off attacks against diving American aircraft, aware they were conceding tactical advantage, unable to do anything else. The P-38's impact rippled through Luftwaffe operational planning. Tactical directives issued to fighter units in early 1944 explicitly warned against pursuing P-38s in vertical dives. Flight training programs added sections on compressibility recognition and recovery procedures. Some German fighter units began adopting diving tactics themselves, attempting to use altitude and speed rather than turning combat. But the German fighters' compressibility limits remained unchanged. They could dive faster than they had, but they couldn't dive as fast as the Americans. The tactical initiative remained with P-38 pilots who understood their advantage and exploited it ruthlessly. German fighter commanders found themselves in an impossible position. They couldn't order their pilots to pursue diving P-38s because such pursuits ended in structural failure or loss of control. They couldn't not pursue because that conceded control of engagement terms to the enemy. The only solution was to intercept P-38s before they gained altitude advantage or to catch them in vulnerable positions during takeoff and landing. Both solutions required perfect intelligence and perfect timing. Perfect anything was increasingly rare in 1944. The individual human stories behind the tactical statistics reveal how deeply the P-38's capabilities affected German pilots' experience of aerial combat. Feldwebel Günther Josten, a Bf-109 pilot with 15 victories, survived a war in which most German pilots did not. In a post-war interview conducted in 1951, he described an encounter over Austria in March 1945. "I had a perfect position. The American was below me, unaware. I began my dive attack, standard procedure. Then he saw me and dove straight away. I followed for perhaps 5 seconds before I felt the buffeting begin. I pulled back on the stick with both hands. The aircraft would not respond. I felt terror, pure terror. I had a decision: continue and likely die, or break off and let him escape. I broke off. He climbed back up and was above me again within 2 minutes. The American pilot was probably 20 years old, no more. I was 28 and had been flying since 1939. My experience meant nothing. His aircraft was simply better at that specific thing. Jostens' words carry no bitterness, only a kind of tired recognition. He had been beaten by engineering rather than by superior skill, and he knew it. This recognition spread through the Luftwaffe like a slow poison, not all at once, not in dramatic fashion, but steadily, encounter by encounter, as pilots learned that certain tactics simply didn't work anymore. The psychological impact combined with material realities to erode combat effectiveness in ways that exceeded the simple mathematics of aircraft losses. German pilots became hesitant to engage P-38s even when they held numerical or positional advantage. This hesitation wasn't cowardice. It was learned behavior based on repeated experience that certain attacks ended badly regardless of how well they were executed. Combat is partly mental. An enemy who makes you hesitant has already gained an advantage before any shots are fired. American pilots, conversely, gained confidence from knowing their aircraft could exit any engagement that turned against them. This confidence produced aggressive tactics. Aggressive tactics produced victories. Victories reinforced confidence. The cycle fed itself. The P-38's influence extended to American strategic thinking about aviation technology. Before the war, American military doctrine treated fighters as defensive weapons meant to intercept bombers. The P-38 helped shift that thinking toward fighters as offensive weapons capable of establishing air superiority deep over enemy territory. This shift required fighters with capabilities the P-38 possessed: range to reach distant targets, speed to dominate engagement terms, firepower to destroy enemy aircraft quickly, and survivability to return from missions over hostile territory. The twin-engine configuration that German pilots initially mocked proved crucial for achieving these capabilities. 2 engines provided redundancy. Twin booms provided stable weapon platforms. The central nacelle concentrated pilot, guns, and ammunition where they were most effective. Everything about the P-38's design that seemed excessive or wasteful served a purpose that became clear only in combat use. This was American engineering philosophy embodied: build capability first, optimize later. German engineering philosophy worked the opposite direction: optimize first, add capability within those constraints. Neither philosophy was inherently superior, but when the challenge was creating an aircraft with unprecedented capabilities, the American approach proved more effective. The technical evolution of the P-38 continued throughout the war as Lockheed engineers addressed problems identified in combat. The J model that introduced dive flaps also added improved cockpit heating, modified oil coolers, and redesigned engine cooling. The L model further refined these systems. Each variant represented accumulated learning from combat experience fed back to engineering teams who could implement changes relatively quickly. This feedback loop between frontline experience and engineering refinement was characteristic of American aircraft development. German aircraft development suffered from rigid specification processes and limited resources for modification. Once a design entered production, changes were difficult and expensive to implement. The Bf-109, excellent when introduced in 1936, was still in production in 1945 with only incremental modifications. The fundamental airframe remained unchanged. Its fundamental limitations, including compressibility sensitivity, remained unchanged. The P-38, introduced to combat in 1942, underwent significant evolution by 1944. Its fundamental strengths, including dive performance, were enhanced. Its fundamental weaknesses were mitigated. By the war's final year, the P-38 was less common in European skies than newer single-engine fighters like the P-51 Mustang, which offered similar performance with lower cost and complexity. But in the Pacific theater, where twin-engine reliability mattered more than in Europe, P-38s remained frontline fighters until Japan's surrender. They hunted Japanese aircraft over New Guinea, the Philippines, and eventually Japan itself. Japanese pilots encountered the same frustrating reality German pilots had faced. The P-38 could dive away from any engagement and return to altitude before the pursuer recovered control. Japanese fighters, built even lighter than German designs to maximize range and maneuverability, were even more vulnerable to compressibility effects. They couldn't pursue diving P-38s at all without risking structural failure. The tactical situation became almost comical in its one-sidedness. American pilots could attack, break off, reset, and attack again, while Japanese pilots could only defend and hope the Americans made mistakes. Over time, the Americans stopped making mistakes. The experienced Japanese pilots who might have exploited American errors were dead, and the replacement pilots lacked the training to capitalize on brief opportunities. The enduring lesson of the P-38's diving capability isn't primarily about aviation engineering, though that's remarkable enough. It's about how technological advantage creates psychological effects that multiply purely military advantages. Every German pilot who broke off an attack against a diving P-38 suffered a small defeat that accumulated into larger doubt. Every American pilot who dove away from a dangerous situation gained a small confidence boost that accumulated into greater aggressiveness. Over thousands of engagements, these psychological effects shaped combat outcomes as much as raw performance numbers. A German pilot who hesitated for 2 seconds before committing to an attack gave the American pilot 2 seconds to see the threat and react. Those 2 seconds often meant the difference between shooting and being shot. The hesitation was rational, based on accurate assessment that pursuing diving P-38s was dangerous. But rationality didn't change the tactical outcome. The side with the technical advantage could act decisively. The side without it could not. In May 1945, as German forces surrendered across Europe, Allied intelligence teams swept through Luftwaffe facilities collecting documents, interviewing pilots, examining captured aircraft. They found extensive German research into transonic flight effects, compressibility problems, and potential solutions. German engineers understood the physics as well as American engineers did. Some German research was actually ahead of American understanding in theoretical areas. But understanding and implementation were different challenges. German aviation industry in 1943 and 1944 lacked the resources, testing facilities, and production capacity to implement solutions to transonic flow problems across operational fighters. Modifications remained theoretical or limited to experimental prototypes. The gap between knowing what to do and having the capability to do it defined much of late-war German aviation. American industry possessed both knowledge and capability. The combination proved decisive. The P-38 Lightning flew its last combat missions in the spring of 1945. By then, the aircraft that German pilots once mocked as a clumsy twin-engine oddity had compiled a combat record few fighters could match. More than 10,000 were built. They served on every front where American forces fought. They shot down more Japanese aircraft than any other Allied fighter. They photographed targets and bomb damage across Europe and the Pacific. They pioneered fighter-bomber tactics. They established air superiority wherever they operated. The distinctive twin-boom silhouette became as familiar to Axis pilots as the sound of their own aircraft's engines. It became synonymous with American air power, with the engineering capability that supported that power, and with the industrial capacity that made it all possible. But above all else, the P-38 represented a specific engineering triumph that changed aerial combat, the ability to dive faster than any contemporary fighter and recover safely. This capability, achieved through methodical engineering rather than brilliant inspiration, gave American pilots a tactical advantage that German and Japanese pilots couldn't counter with superior skill or courage. It proved that modern warfare was increasingly a contest of engineering and industrial capacity rather than individual martial prowess. It proved that democratic capitalist societies could produce weapon systems equal or superior to those produced by authoritarian states that claimed inherent superiority. These proofs mattered in 1943 and 1944, when final victory remained uncertain. They mattered even more afterward, when the world rebuilt itself and chose between competing visions of how societies should organize themselves. 75 years after Franz Schiess watched that first P-38 dive away from his pursuit, the lesson remains relevant. Technical advantage in warfare isn't usually total, it's specific, applying in certain situations under certain conditions. The P-38 wasn't superior to German fighters in every flight regime, but it was superior in one crucial regime: the vertical dive, the escape maneuver, the tactical reset that allowed losing pilots to survive and winning pilots to dominate. That one advantage, properly exploited, proved sufficient. Modern engineers studying historical aircraft performance still examine the P-38's dive flaps as an elegant solution to transonic airflow separation. Modern pilots studying aerial combat tactics still reference P-38 boom and zoom tactics as exemplars of using technical advantage to dictate engagement terms. The aircraft itself disappeared from military service decades ago, retired to museums and air shows. Its lessons endure because they transcend the specific technical challenge of 1940s fighter design. The lasting symbolism centers on American industrial philosophy: identify the problem, engineer a solution, test it, refine it, implement it, and move forward. Not elegant, not theoretically pure, but effective. The dive flaps that made the P-38 survivable at transonic speeds were not aerodynamically optimal. They added drag, they added weight, they added mechanical complexity, but they worked. They solved the problem of compressibility-induced loss of control in a way that German and Japanese engineers, working within their different industrial and philosophical frameworks, never managed to solve operationally. The pragmatic American approach of good enough to work now beat the perfectionist European approach of theoretically optimal but not yet implemented. War rewards solutions that work over solutions that should work but don't yet. Engineering rewards the same thing. On January 17, 1943, Franz Schiess recovered from his near uncontrollable dive and climbed back toward altitude, his hands still shaking slightly on the control stick. The American P-38 was already gone, disappeared into the vast sky over Tunisia, its pilot likely unaware of how close he had been to a German ace's guns. Schiess would fly many more missions before war's end. He would survive, unlike most of his fellow pilots. But he never forgot that moment when he pushed his aircraft into a dive and discovered that American engineering had rewritten the rules of aerial combat while German pilots were still flying by the old rules. He never forgot the helpless feeling of watching an enemy aircraft pull away while his own machine shook itself nearly to pieces. He never forgot the lesson that technical advantage, properly exploited, trumps skill and experience. It was a hard lesson. It was perhaps the hardest lesson for a skilled professional to learn, that sometimes, despite your training and your experience and your courage, you simply cannot match what the other side's engineers have made possible. The twin-boom silhouette of the P-38 Lightning became a symbol during the War of American technological reach. But its deeper symbolism emerged only through combat experience. It symbolized the victory of systematic engineering over theoretical elegance. It symbolized the power of iterative refinement over perfected initial design. It symbolized the advantage of industrial capacity married to scientific method. Most fundamentally, it symbolized the ability of democratic societies to organize complex technical efforts and produce results superior to those achieved by authoritarian states that claimed inherent efficiency. These were not the lessons German pilots expected to learn when they first encountered the odd twin-boomed fighter over Tunisia in early 1943. They were not lessons German ideology prepared them to accept. But the sky enforced its own truths regardless of ideology. The aircraft that could dive faster and climb back survived. The aircraft that couldn't, didn't. The pilots who adapted to this new reality survived. The pilots who couldn't, didn't. War has no interest in ideology. It cares only about capability. The P-38 Lightning had capability German fighters lacked. That capability, achieved through unglamorous engineering persistence, proved decisive in thousands of individual combats and accumulated across years of warfare, helped achieve air superiority that made Allied victory inevitable. The mechanics of that victory involved tens of thousands of factors beyond any single aircraft's capabilities. But among those factors, the P-38's ability to dive away from danger and return to fight again stood out as a specific, measurable advantage that changed how aerial combat functioned. It made aggressive tactics safer for American pilots. It made defensive tactics insufficient for German pilots. It transformed air combat from a contest of pure skill into a contest where engineering capability determined engagement outcomes. This transformation was neither sudden nor obvious. It emerged across thousands of individual engagements where American pilots dove away and German pilots couldn't follow, where American pilots reset and attacked again while German pilots could only defend. The accumulated weight of these small advantages created a large strategic advantage. American fighters could operate over enemy territory with acceptable loss rates, while enemy fighters could not prevent them from doing so. Air superiority followed from this reality. Allied victory followed from air superiority. In the end, Franz Schiess and his fellow German pilots were correct about one thing. The P-38 Lightning was wasteful, complex, expensive, and over-engineered by German standards. It used two engines where one might suffice. It had elaborate systems for problems German designers solved more elegantly. It represented American abundance in material form. But that abundance was precisely the point. America could afford to over-engineer, to build fighters with capabilities exceeding immediate requirements, to add systems that solved problems proactively rather than reactively. German aviation operated at the edge of resource constraints throughout the war. America operated well within its resource capacity, which meant American engineers could pursue solutions without constantly compromising based on material limitations. The P-38's dive flaps, its strengthened airframe, its refined systems all represented engineering work done not because it was barely sufficient, but because it was comprehensively excellent. That difference, multiplied across thousands of aircraft and dozens of weapon systems, defined why one side won and the other lost. The sky above Tunisia on that January morning in 1943 held no malice, no ideology, no judgment. It simply imposed its physical laws equally on all aircraft flying through it. The law of compressibility applied to Messerschmitts and P-38s alike. But American engineers had learned to work within and around that law in ways German engineers had not yet managed. That made all the difference. That made Franz Schiess break off his attack and return to base with nothing to show for his mission. That made thousands of similar encounters play out across the war's remaining years, with American pilots increasingly dominating the vertical dimension of aerial combat. That made the twin-boom silhouette of the P-38 Lightning something German pilots learned to respect, then to fear, then to avoid when possible. Engineering, in the end, proved as decisive as courage. Perhaps more decisive, because courage without capability leads only to valiant failure, while capability enables courage to achieve victory. The P-38 gave American pilots capability German fighters lacked. Everything else followed from that fundamental advantage.